I need you guys to put a initial next to your name, basically. And I'll have that out. I just printed it, but I'll have it out every morning when you come in so you can sign in. So, sorry, I said 15%. It's 15 points, so somewhere around like 10% of your grade. So attendance matters. So if you don't like waking up at 8:30, drop this class. The other thing is that all your assignments are going to be due on Saturdays. So there's basically two assignments every week. One is a little short quiz that covers the textbook. The other one is a more expository piece where you essentially use this video interface and give a little response. It's something like somewhere between an essay and a video assignment. They're really short, like 2-minute assignments, but you'll basically respond to something that you watched. So every week there's a watch list. That's another thing. If you don't like watching things, drop the class. There's a lot of watch in this. There's not a lot of reading, which is nice. So the textbook's pretty simple. It's an online textbook. It's free. But there are a lot of watch items, right? So what you're going to be doing every week is short little quiz and a short little 2-minute response to something that you watched off the watch list, basically. If that doesn't sound fun to you, drop the class. See, what else do I want to say about that? All these assignments are due on Saturdays, so don't pay any attention to anything you see anywhere else. I've tried to lay it out in the syllabus for you, which is available on Moodle. Check out the syllabus. It'll give you a rough idea of how the weeks are going to progress, but generally speaking, everything, including your final project, is going to be due on Saturday. Everything is due on Saturday of the week that it's written. Any questions about that? It's 10 p.m. on Saturday, too. I'm going to grade everything on Sundays, so here's how this works. If you don't do an assignment on Saturday, like say you just don't do a quiz because you got busy, that's fine. Moodle doesn't compute your missing assignments as zeros essentially until the end of the semester. So don't mislead yourself, right? If you haven't turned in any assignments and you see that you have 100% in the class because you did one of them and you got 100% on it, don't think that you're sailing through this, right? They're going to turn into zeros at the end of the semester, so keep an eye on that and pay attention. So I shudder to say this, but if you turn those assignments in by the end of the semester, you'll be okay. I feel bad saying that. They are due on Saturday, and I will grade especially the video responses on Saturday. If you don't turn a video response in on Saturday, you got to email me and tell me it's late, and I'll give you some, I'll give you partial credit for turning it in late. I won't know otherwise, though, unlike the quizzes. The quizzes are automatically scored. If you turn in a video assignment late, email me after Saturday. Okay. All right, that's all the boring stuff, I think. There's no final exam in this class. In fact, there's no exams at all, which is probably a reason not to drop the class. But you do have to do a pretty substantial investigation presentation type video assignment. Yeah. Really? Yeah. Oh, boy. All right, well, we'll fix it. That's easy to fix. Sorry, guys. I'm sorry about that. Yeah, I think I didn't publish it. It's true. It's my fault. Okay, I'll publish it right after this class. That is a good point, though. But guys, if you discover anything like that, so I inherited this class from somebody who taught it last year. This is my first time teaching this class at this university. So if you see something weird in the syllabus, please email me. Right? If you notice that Moodle's not online, email me. It's amazing how these things just kind of slip along and nobody points them out. So email me. If there's anything weird, something doesn't make sense, please email me. If you want to just talk about anything that we've gone over in class, email me. We can Zoom. I don't live anywhere near here. I live sort of by Grants Pass, so I'm not going to be having office hours here, but if you want to Zoom, we can do that. All right, questions about all of that kind of businessy stuff? Yeah. Yes. Sorry, I'll publish both. The lab, yeah, if you're taking the lab, one sec, I'll get to you in just a second. If you're taking the lab is somewhat autonomous. It's pretty cool, though. There's essentially an online Sky program that allows you to surf through the solar system and so forth, and I think that'll be really cool. The one last semester was really fun anyway, so I did it alongside. I haven't done this one yet, but it's going to be cool. So it's cheap. I mean, it's a $35 program you got to buy. Maybe it's $30. But it's a pretty it's a pretty easy and fun exercise, but it's entirely online. Yeah. Okay. Okay. I don't know. This is Sean. I don't know what the book said that.
Like the bookstore said.
Oh, the bookstore.
There might be a free one.
There is. The book is free. It's online. It's called Open Stacks. Yeah, Open Stacks. It's online, and that's actually a really cool thing because it's constantly updating. And so what you'll find actually, and what's really exciting about this class, so I'm going to sell it a little bit now. This is a really awesome class because planetary sciences and astrophysics is one of the fastest changing sciences on the planet, right? It's also the one that's the least tied to politics and money and everything else. And so it's a really fun and quickly changing science. So the fact that it's an online free textbook is really cool because they're updating it constantly. And the paradigms are changing under our feet. And that's what's going to be really fun about this class, I think. All right. Any more questions about that business stuff? I have one more thing that I want to do. So some people last semester complained, at least one person complained, that they didn't have a chance to hang out with one another. So they didn't get to know anybody in their class. So what I'm going to do, well, I wanted to do something more elaborate, but the department has no money for us. So what we're going to do is once a week, let's do it on Thursdays, let's say, so I can remind you on Tuesday. We're going to just hang out here at 8 a.m. I will bring a Mr. Coffee. You will bring your own beverage, whatever. I will have refills, and we will hang out, and we will mingle. We will talk astrophysics with one another, and we can get to know each other a little bit better. So whoever wants to come to that, it's not mandatory, but I am going to basically make a little salon out of this place at 8 a.m. every Thursday. So yeah, come. If you're into that, I really think it'll be good. I really want to get to know you guys. I can't do that otherwise. There's too many of you. And I think it'll be really fun. So even if 3 people come, I think it'll be fun. If all of you come, it's going to be quite a party. But we'll see. So we're going to do that. Starting on Thursday, I'm going to go after this and try to see if I can get a large Mr. Coffee Maker type thing. And yeah, cool. I'll remind you of that again. So big things to remember. For me, publish the Moodle. For you guys, don't forget to sign the attendance thing before you leave today. And it will always be there on the back desk. And yeah, Thursday we'll have a coffee hour, or coffee half hour at 8 a.m. right here. And if too many people could show up, we might go up to the lounge upstairs, but let's start doing it down here. I like this speaker system and stuff. So, okay, let me see what else I wanted to go through here. Okay, so today, this week in general, I'm going to crack open our whole discussion of solar physics with our own sun. I think we're going to spend a couple of weeks on our sun. This week, today, we're going to hopefully just do an overview of the different pieces and structures of the sun, how we know what we know. Thursday is going to be really exciting because I want to dig into the history a bit and try to explain how we think we know what we know. Because that's one of the funny things about science is we don't actually know anything for certain. And as we move through time and as we learn more, we come up with better and better explanations. And so this is actually one of the coolest parts about science is that we're never completely right about anything. So when I present these ideas to you guys, moreover, when the textbook presents you an idea, you have to keep in mind this is just our best conception of this phenomena at the time. So what I want to do on Thursday and what I'm going to keep doing throughout this course is really explore the history of these ideas. How did we come up with this particular conception of the sun that we have right now, which might be completely wrong? And almost certainly is wrong to some degree because that's how science works, right? The way that we thought about the sun 1,000 years ago was complete lunacy compared to the way that we think about it now. And quite honestly, 1,000 years from now, they will probably think of the way that we think about it now as complete lunacy. This is just how science works. And I think it's really exciting. And actually, the only way that we can make sense of it is by looking at those little updates along the way and looking at the battles that have happened. And sometimes people agree to premises that false 100 years later. And there's a number of anecdotes we can explore about that. So think it's really important to go back, particularly when it comes to the sun. One of the most troubling aspects of the sun is how it generates its light, right? So we'll get into this in just a minute. I don't want to spoil all the details, but the light from the sun is very particular. The processes that are necessary to generate that light are not, they're not readily conducive towards a ball of gas burning in the sky, right? So we have balls of gas burning in these lamps up here right now. If you were to take a prism and split this light, so you could see the different colors that make it up, this white light and these, you would see nice little lines, right? Because what happens is gases give us nice, beautiful lines that each one of the gas atoms can only wiggle in a few directions, right? It's completely unbound to others. But say we have, I think back here we have some incandescent bulbs, right? They're filaments of metal that are heated with electricity and they glow. Well, the glow that they give off if you split it with a prism is completely continuous. It's like a rainbow. The reason for that is because the lattice of the metal is able to vibrate in essentially an infinite number of ways, right? Not only can the atoms vibrate, but the whole thing and every piece of it can vibrate. So you get a continuous rainbow of light. What's puzzling about the sun, despite the fact that we treat it as a burning ball of gas, is that the sun gives off a continuous spectrum as well. And so the convolutions necessary to give us that continuous spectrum from a ball of gas are troubling. They're mathematically troubling, and the science is completely on the move. And it's a really interesting story, and so that's what we're going to spend a lot of time on this week. But first, I think that I need to introduce myself to you guys. I haven't done that yet. Your first assignment actually is to introduce yourselves to each other and to me. So you're going to make a tiny little video about that this weekend, which is due on? Yes, exactly. Okay, so quick little background about myself. If I can make this thing work. Oops. Computer is absolutely struggling. Okay, that's me. All right, so look, I started teaching back in New York when I was a grad student at Columbia University, and that's where I did both my master's and my PhD. My background is actually in material physics, which I think should make this really interesting because astronomy and astrophysics has always kind of been a hobby for me. I didn't want to go into it for my actual degree at the time because I felt like it wasn't grounded enough in things that we could actually play with on Earth, and I felt more comfortable with touching things and actually building machines and stuff like that. So all my work was in engineering. We built these little machines that run on evaporation. They're really cool. We use biomaterials that expand and contract in evaporation gradients. And so, you might think this is kind of weird to have like a material scientist teaching you about the sun. But I guarantee you it's going to make for a more interesting perspective than you'd probably get just from your textbook, right? So every process that I see in physics has to come down to material interactions, right? What is physics? What is physics that separates it from, say, metaphysics, or separates it from literature, or separates it from biology? And I would argue that the difference is that physics is always about bodies interacting with one another, some sort of body, right? And so this gets lost a lot of times on people who spend their whole time looking through telescopes and they're just examining light and they're not thinking about actually the material interactions that allow them to see those. How does light work, right? This is complicated. We're going to get into it. But certainly involves some sort of bodies interacting with one another. So I think that's fair enough. The other thing I want to tell you about myself, and you'll figure this out eventually anyways, my wife and I run a podcast where we get to talk to all sorts of cool people. And I'm going to bring this in a number of times. I'll put some of these podcasts that are relevant into the Moodle under the watch list. You can respond to them if you're so inclined. But we do get to talk to a lot of really cool scientists, especially people at NASA who are, I posted one this week where we talked to Nikki Fox, who's the director of the Parker Solar Probe. This is the first time that the NASA's actually gone out and touched the edge of the sun, which is really cool. And so we have the opportunity to ask these scientists who are actually out there studying the different topics that we're going to cover in this class. We can actually ask them questions, which is really cool. Because I think some of the really interesting stuff is the stuff that isn't published. It's the problems, right? It's the issues, the things that don't make sense, right? Those aren't going to make headlines because, the funding strategy is that NASA is awesome and everything we find is cool, and therefore give us more money, Congress, which is totally a valid perspective. I totally understand that's how it works when you're inside of institutional science. So look out for that. That's going to be happening. So the podcast is called Demystify Sci if you want to check it out. All right. So if we want to study the stars, our best chance is to understand our own star. And I forgot one more thing that I want to mention. One more time, I'm going to try to talk you out of dropping this class. Okay, I don't list things on the board, right? So if you want to sit there and take notes of things that are on a list, you're probably going to hate this class. I also don't totally, I don't totally know what I'm going to talk about when I get up here. I have interests. I've read the textbook. You guys have the textbook. You don't need me to go over the textbook again. What I try to do is explore things that I don't understand yet, and I think those are going to be the most interesting things because as I come to grow through them, hopefully you guys will grow with them too, and at least if you see how that's done, maybe you can apply it to your own particular interest in this. So this is not a class where I'm just going to sit here and lecture, but I am going to explore these ideas out loud. If that sounds boring to you, try a different class. So anyways, back to the sun. So there it is. So the line from your textbook goes like this. The sun, like all stars, is an enormous ball of extremely hot, largely ionized gas shining under its own power. Okay, so what do they mean by consensus? Anybody? Yeah. Yeah, it's generally agreed upon. Now, the funny thing about that concept is that scientists almost never agree on anything, actually. If you go to a solar physics conference, you would be hard-pressed to put two people in a room who actually agreed on almost anything, right? So what we mean is that this is the best idea that we have right now, essentially, right? This is the idea that people are most comfortable with. And so that story that they said, an ionized ball of burning gas, well, what does it mean to be ionized? Has anybody ever heard that before? Right? That's fine. Yeah? Yeah? What's it mean? Yeah. Cool. All right, so I'm going to assume most of you guys are non-science majors. That's totally fine. So the outer surface of the atom is essentially called the electron. This is a bit complicated because the electron is sort of a reification of that, of a process into an object. What I mean by that is that sometimes we have a tendency, especially in advanced physics, to take whole ideas and turn them into little actors that we can move around. The surface of the atom is moving in a particular way, and we call that the electron. What's really interesting in ionized materials is that a gas, like say this gas that's in these lamps up here, if I shut off the electricity to it, right, if I stop powering them, it goes dark, right? Gases are generally non-reactive. They're dark. They don't do a lot. It's these inert gases that are in this. I'm not sure what substance is particularly in this. Now, what happens that's really interesting is when you apply a really large voltage to these lamps or to a gas, is that the gases begin to act a little bit like a metal, right? Like you said, the electrons are delocalized, right? It's said that they're stripped from their nuclei. In other words, the surfaces of all of these atoms join up and act together as one. That's really interesting. Okay, so we know the sun is electrically active. We know that electrical processes, particularly electromagnetism, play a huge role in determining the structure, especially the surface structures and what's going on. And we'll talk a little bit about the catastrophes that result from those surface structures in their dynamicism and how they collapse and reshape, which obviously impacts our Earth. So the sun certainly has this metallic character, right? It's able to conduct electricity, which is really interesting. I think that's the takeaway here. And then the consensus about the gaseous nature is really interesting too, and we'll talk more about that on Thursday. Needless to say, they say it is a plasmatic gas, right? Well, what is a plasma? Does anybody have any idea? The plasma is a really, really interesting word. It's kind of one of those words that can mean whatever you want it to mean in any situation. It's perhaps the fourth state of matter, I've heard it said. Certainly, it involves ionization, right? This metallic character of the gas. But generally speaking, we're thinking of very rarefied gases, so thin, that have conductive properties. This is a plasma. But what's really weird is if you start digging, if you start studying plasma, right? If you go to graduate school and you start reading a graduate textbook on plasma physics, you start to find that plasma can also mean a liquid-like body, right? It can also approximate solid-like character with ripples and waves in it. And so it's kind of one of those words that's actually less useful than it appears on the surface because it's not entirely clear. It can essentially mean a whole category of different substances and phase states. So we'll take that with a grain of salt. So yes, the sun is one of these, is thought to be, by consensus, one of these giant plasma balls, which is quite interesting, which, only narrows it down just so much. And on Thursday, we're going to get into, like I said, more how we know, how people have come to the consensus that it is so. And it's a really interesting story that involves politics and experimentation and refutation. But yeah, the story is still going on. Come on. Okay. Oh, there's a little lag here. All right. So it's thought that the sun doesn't have a solid surface, which is the first thing that's quite interesting. Although it does appear to, which is even more confusing. It does seem to have some structure to it, which is a very difficult thing to reconcile for this gaseous conception because you have different layers of it. And I want to walk you through each one of the layers very quickly, but real briefly, just to give you a sense of scale here, the Earth, that is not a reasonable size for the Earth. So in reality, the thing is about 110 times the diameter of the Earth. All right, it's really, really big. The Earth is pretty big. This thing is 100 times that. That makes it something like 300,000 Earth masses as well. Actually, the Earth is far more dense than the sun, which is really surprising. The Earth is, I think, the most dense body in the solar system, which is very, very interesting. How it is that it didn't end up in the center of the solar system is a whole other mystery. We generally think of the sun as being one astronomical unit away from us. So when we talk about the distance from us to other stars, this will matter later. We're going to describe them in terms of astronomical units. The sun to us is one astronomical unit. This is completely arbitrary. It represents about 149 million kilometers. Yeah?
When you say the Earth is denser than the sun, is that refer to the core of the sun or the surface?
Yes. It's an average. Right, so certainly there should be some points inside the deepest parts of the sun that's something like 24 grams per centimeter cubed or something like that. The Earth is about 5, if I recall correctly. So on average, yes. The outer part of the sun, I'm not sure where that, usually when people say they bound the sun, like when I just told you the diameter, what we're talking about is the photosphere. That's the visible surface of the sun. And we're going to keep beating on that concept because the concept of a surface is an unavoidable situation. It's often argued that the surface of the sun is an optical illusion. There is no surface to the sun. We'll play with both perspectives. We'll see what's up. But when we say the diameter, we're talking about that edge. So what's really interesting is if you don't take it from that edge there, if you include the whole atmosphere of the sun, the atmosphere of the sun is thought to be extraordinarily dense. Like, I think something like 10 to the minus 16th atoms per centimeter, something outrageous, right? Almost nothing there in the corona. So, yeah, it's dynamic and it has this layered structure. Some parts are denser than others. That makes sense. Okay, so let's, we're gonna work our way down into the sun first, and then we'll spend a little bit of time at the end on the atmosphere itself. So there's 4 distinct parts of the atmosphere. This is what we're gonna see when we look at the thing. And actually, this part that you see here is essentially the corona, right? So you can see this during an eclipse. It's the very rarefied outer portion of it. So there's 4 distinct parts. There's the chromosphere, there's the transition region, there's the corona, and then there's the heliosphere. Now, this is where things get really weird. The heliosphere is actually something that we are being bathed in right now at this point. So the sun technically extends throughout the entire solar system, all the way to the edge of the solar system, and then wraps back around. So there's a really interesting sheath of electromagnetically active substances, ionized atoms, which are bathing the entire system, especially at the equatorial plane. And so the sun, putting a boundary on the sun is a really interesting discussion. I can't get enough of that, and you'll see why soon. All right, so the photosphere being our proper surface of the sun, this is what looks like a surface anyways. We'll talk about it more in a second. Right above that is the chromosphere. So this is a really interesting point because this is where the atmosphere is very cool, actually, and then it heats up to an extraordinary degree. And this is actually one of the other most bizarre, strange mysteries of the sun. The atmosphere is so much hotter than the surface, the effective surface of the sun. I mean, millions of degrees, whereas the surface is like something, I think effective temperatures around 5,000 Kelvin, okay? This is very, very bizarre. How does this happen? We'll play with that soon. And is it even appropriate? Are we treating it right? What does temperature mean at that point, right? You gotta keep in mind, all we have when it comes to the sun is what we can see. And I mean, we can see things with telescopes that we can't see with our eyes, but essentially all we can do is measure radiation. And so all of the information and the statements we make are based on that radiation, essentially, right? So there's a huge question. Is the temperature of the rays of the sun, right, are those actually reflective of the temperature of the body itself, or is there some other process going on? And it's not so easy, actually, to say so. If you look, when people talk about the temperature of the sun, they always say the effective temperature of the sun. And we can get into why that is, but it's essentially what's apparent, right? It's if we apply our laws, particularly our laws of black body radiation, to the sun, what temperature do we get out? Okay, we get this temperature. What if the sun's not a perfect black body? Well, it does appear to have a perfect black body curve, and we can get into that. But what if there's something else going on, right? What if the convection, what if there's other processes of dissipating heat that aren't just putting it into the rays that we're able to read out with our telescopes and read out on Earth? In other words, what if all of the heat isn't going into the light and we are actually looking at a temperature that is not completely accurate? It's gonna be effectively, there's some missing heat in the system, and that's an interesting argument we'll play with. Okay, so the heliosphere, I told you a little bit about that. This is this enormous boundary which presses out way beyond the planets, way beyond the outer trans-Neptune objects, all the way out to the leading edge of the solar system. And this contains material that originates in the sun, and it's participating in the magnetic field effects of the sun as well. So there is an argument to be made that the sun essentially extends all the way out to the edge of this place. By the way, that edge is really far away. So the Oort cloud, which is some consider this, it's a theoretical wall of material at the edge of the solar system. Some estimates put that thing at close to a light year away from us, right? I mean, think about how long just think about, it travels at 300,000 kilometers per second. Think about a year of travel at 300,000 kilometers per second. I mean, this stuff is unbelievably far away. Our solar system is unbelievably large, right? So, and I think we forget this, right? You go outside and you look at Mars or something, and you don't think, wow, that's actually what Mars looked like 15 minutes ago, because that's how long it took. It's that far away to get the light here. So the heliosphere is the outer surface. And it's actually, if you look at the equatorial plane of this material that's coming out of the sun, it forms this very beautiful vortex type business. And when we get into some of the stories, particularly the early stories that we told ourselves about how solar systems work and form, many of them from our venerable scientific ancestors, let's say, focused on the vortex nature of these systems. Turns out to be sort of the case. Seems out it actually is part of the story. All right, so let's talk about light for a second, because and your textbook kind of glosses over this. There is a chapter in your textbook, by the way. If you know nothing about light, I highly recommend it. It's linked in this week's chapter. I think it's called spectroscopy, something like that. Every single thing that we're going to talk about in this class, all of the evidence that we're going to talk about in this class have to do with light. Radio waves are a kind of light. Infrared radiation is a kind of light. Gamma rays are a kind of light, right? Not all just visible light. Now, there's something really remarkable, and I talked about this last semester, so excuse me if you've already heard this, but look, our atmosphere is an incredible piece of coincidence, right? It lets visible light through, but almost nothing else. And that's a really good thing, right? If you look at the absorption spectrum of our atmosphere, that is what light it takes up and won't let go of. It takes almost everything that's dangerous, right? In particular, ultraviolets and things that are gamma rays, X-rays. It grabs all that stuff and doesn't let it go towards us, right? It either redirects it or it downshifts it into something more palatable. And it lets a few radio waves through from the far end of the spectrum. So we can think of light, large wave radio waves, all the way down to our visible light, down to tiny little X-rays and gamma rays, the things that will essentially shake your DNA to pieces. And for some reason, maybe we couldn't have evolved otherwise, but our atmosphere only lets through the things we can see. But all of these different colors, from radio waves down to X-rays, are going to prove very important in our understanding of the sun. And so I want to just give you a little primer on that today of how we know what we know from the different spectra. And I opened it up a little bit earlier, but I told you a bit about the difference between gases and solids. We'll save the photon for another day. So this is essentially what happens when you split the sun into, you take a prism and you split it, and essentially what a prism does is it takes the rays of light. So light travels in photons, which are these ray-like projections, let's say. By the way, I guess we can't get away from this. So what is light exactly, right? Is it just these little cannonballs that are shot out of atoms? That's usually how it's drawn in textbooks, but I don't think that that's quite right. I think a better way of looking at this, and my friend who's a Caltech professor who works a lot on this mathematically, has begun to think about it as a conversation between atoms, right? So atoms are connected to one another. This is apparent because of gravity. You're sticking to the floor right now. How do you think that's possible? Well, you're somehow connected to the other atoms in the floor, the ones in the earth, and so on and so forth. So atoms appear to be connected to their neighbors, and they seem to be having some sort of energetic conversation with one another. And we don't have any certainty about the details of that, but light seems to be some sort of a pressure that occurs between atoms, and it has a torsional helical aspect to it, right? It has an angular momentum. It twists, right? So the atoms are constantly twisting and pushing on each other. How they're doing that is largely encoded in mathematics right now. And so giving you a material explanation for that is something that there is no consensus idea of yet. So that's a huge thing if anybody wants to work on it, and it's an interesting topic. But essentially, light is some sort of conversation between atoms. There's somebody who's very energetic over here, an atom. There's an atom over here, and somehow this one is pressuring this one to get in phase with it and link up and take some of that energy up. Okay, so what happens when you send a bunch of different kind of light, let's say white light, through a prism, is that the different wavelengths, the different energies of light are going to travel at different speeds through that glass, okay? They slow down, right? The more energetic ones are going to go faster, the less energetic ones are going to go slower, and what happens is that some of their forward momentum is lost, and they kind of bend off at an angle, right? You can just imagine it. If you just like shot a gun into a tank of water, the bullet would just kind of go, right? So this is the same thing that's happening with light in a prism. The wavelengths are getting separated because they have different energies, right? They have different amounts of heft to them, you know. If you shot a really high-powered rifle into a water, and then you took like a little .22 plinker and shot it into the water, the high-powered rifle is going to go further. Same idea with light, okay? So the prism splits the light into its different energies, which we see as colors. They also could just be represented as wavelengths. We obviously can't see colors with radio waves. So there's something else interesting you notice here, though, too. The sun has this beautiful continuous spectrum, right? But you see these little tiny black lines on it as well. The black lines actually represent the atmosphere of the sun, some of our own atmosphere, but largely the atmosphere of the sun screening out certain frequencies, right? So one of the most important laws of radiation is that if you can absorb some color, you can also emit that same color. So in this case, what we can do is we can look at what colors are being absorbed here. These lines, they're actually called the Fraunhofer lines. These are the lines that tell us the composition of the gas molecules in the sun, because what we can do is we can go to our laboratory on Earth and we can take different elements, right? We can take sodium, we can take hydrogen, we can stick those in a flame, and we can see that they only give off one line of color. They only give one frequency. Maybe each atom has a few different ways it can wiggle, so it'll give off 2 or 3 discrete lines. So we have fingerprints for each of the discrete atoms that we can map here on Earth. And what's incredible is that they map perfectly onto the atmosphere of the sun. So for each one of these little black lines, we can say, okay, this is some particular element that's in the atmosphere of the sun. Now, explaining the continuous spectrum of the sun with the gases is a complete nightmare. And we'll deal with that, I think, more when we get into the fusion story for next week, because it's ultimately tied into the fusion story. Now, you might also say, why is Dr. DeLay so hung up on this gaseous sun business, right? Well, it plays very heavily into the stories that we tell ourselves cosmologically, because by the end of this course, we're going to be talking about cosmology. What the heck is, does anybody know what cosmology even means? What's the cosmos? So like cosmos and chaos are 2 diametrically opposed concepts in ancient Greece, right? Do you know what chaos means? What's chaos? It's madness, right? It's everything we don't understand, right? It's like, what's going on? Chaos. Cosmos is the opposite of that. It's putting order upon the universe, right? It's like, oh, I understand how light works. This isn't just some magic stuff all of a sudden, right? And so cosmology is our quest to put our human lives in the context of the greater universe, right? Now, it turns out that our cosmology today is almost identical to the cosmology that's existed in every culture since the beginning of time, which is essentially that there was a birth moment and there will be a death moment of everything all at once, just like our own human lives. Now, this is a very important story, obviously, in terms of reconciling who we are in the universe, but there's a number of biases that go into that. And the way, actually, that we conceive of our sun, this process that allows us to get a continuous spectrum out of a ball of gas, is the same argument that is used to explain how it is that the early moments of our universe were able to generate this perfect cosmic black body spectrum, which is called the cosmic microwave background radiation, which is essentially the strongest, most fortified pillar of standard cosmology today. So this does matter. It's going to matter throughout our course. We need to understand the argument for how anomalously a ball of gas can generate a continuous spectrum because it's never been done on Earth. No one can take any ball of gas in a laboratory and create a continuous spectrum out of it. However, astrophysicists insist that this is what's happening on the sun. And not only that, the same mathematics that they use to achieve this continuous spectrum is what's used to justify the creation myth that we have today. And so that's a really, really fascinating story. And I'm not saying they're wrong about that. I'm saying that it is a really, really difficult argument for them to make. And so I want everyone to come up to speed on that as we go forward. Cool. All right, so the Fraunhofer lines. So who was Fraunhofer? He was this English chemist from the early 1800s who essentially was the first person who figured out that these lines existed. He was able to actually make these spectra with his telescope for the first time. He made friends with, well, I'm not sure they were friends, but these two other gentlemen who we're going to talk about at great length, Kirchhoff and also Bunsen. So you guys have heard of Bunsen burners, right, in laboratories? Even if you've never taken a science class, you've probably heard of a Bunsen burner. So Bunsen came up with the Bunsen burner. He and Kirchhoff were the two that actually sat around burning things and looking at the particular lines that they gave off. And it turns out these two were actually the first ones to kind of put it together that, hey, I think what Fraunhofer has reported as these lines in the solar spectrum actually correspond to elements that we have down here on Earth. So that's pretty cool. I'm going to get really into the history of that on Thursday, but let's go a bit deeper down below the atmosphere. So the way that I hope that you understand a little bit about how we understand the composition of the atmosphere. Your textbook outlines the composition a bit better. Needless to say, the sun is almost entirely made out of hydrogen with a fair amount of helium also. Actually, helium was discovered in the sun first. If you think about the Greek word for sun, helios, that's where we get the word helium from. But the composition is very similar to, say, Jupiter. It's actually almost identical to Jupiter, which is really fascinating when we start thinking about what Jupiter is, because essentially Jupiter is almost a star, right? It didn't have enough mass to actually ignite, but it's very similar, okay? So as we dive down, we have a few different layers we need to check out. So we talked about the lower layers of the chromosphere, the cooler areas. Then we go down through the photosphere. There's this radiative zone. Oh, sorry. Next, there's actually a convection zone. And this is thought to be where heat is rising, where there's a lot of churning going on. There's this mysterious radiative zone, and this is where our magical process of the changing of the creation of the continuous spectrum is thought to happen. And the way that that's thought to happen is that these photons, which are created during fusion at the core of the sun, are thought to bounce around for something like millions of years, right? And what happens is as they bounce around, they can't find their way out of the sun, and they lose energy, in such a way that gives off a perfect black body spectrum at the end of the day. So we'll play with that idea a bit longer, but those are essentially the regions of the sun that we need to be aware of. It's also worth pointing out, all of the things that we see going on here are essentially happening on all the other stars too. This is just our best specimen. Our star is essentially a run-of-the-mill star. It's a very, very common type of star. It's a main sequence star, a G-type star. We'll get into what all that means later, but essentially we can think of most stars as being like this. There's different times in their birth and death where they're going to look differently. Very large stars are going to look differently, but for the most part, stars look like this. Actually, most stars are smaller than our sun, which is interesting. Almost all stars are dwarf stars, but compositionally, this is essentially what we're looking at. So let's keep going. This is our effective surface of the sun. This is where the light that we see for the most part is emitted from, the photosphere. The effective temperature of the photosphere is about 5,800 Kelvin. Let's see if I can get this to appear. Okay, cool. So there's a couple of really interesting discoveries that were made when studying the sun originally. And these will matter more than you can believe later when we get into this, but I want you to be aware of them. So one of the first things that was observed was that these are black body curves, first of all. So people were originally, before they had the lines that would tell them about the atmospheric composition, all they had was this black body curve, which let's say it's essentially close to the largest peak here. And what they noticed was, well, what is a black body and how did they do all this? So what people noticed was that if you took some sort of object and you heated it, it gave off light. And it seemed to give off light whose color was dependent upon how much you heated it, right? And so all of the original thought was that, and it gave off this particular spectrum of light, right? And what's interesting is that the peak wavelength, where you get the most light, the color where the most light is coming from, tends to shift as the temperature goes down, right? So there was a guy named Wien who came up with this relationship and found that this displacement was proportional to temperature. A couple of other people came along, Kirchhoff and Stewart came along and essentially said, hey, you can actually get the temperature just from the wavelength itself. And then Planck came along and fitted a nice curve to it. And all three of these guys essentially paved the way for a situation where we were able to say that the energy of light is proportional somehow, well, directly to the frequency of that light, to the color. This was a great deal of work that was all predicated on the understanding of black bodies here on Earth. And so, you know, black bodies are going to keep coming up over and over again, and we're going to deal with them more on Thursday too. But a black body essentially is this idea that if you take an object, you heat it up, and you put it in a perfectly dark cavity, right? They used to use these carbon soot-covered boxes, and you put that body that's glowing hot into that black body. Well, what happens is that eventually it reaches thermal equilibrium with the cavity. And the cavity begins to glow at the exact same color once they're in thermal equilibrium. And you can measure that wavelength, and you can get the temperature of the black body, and it's a perfect, perfect experiment. I mean, once the objects are at thermal equilibrium, it gives you the exact temperature, this black body spectrum. Now, is that what's happening at the sun? Well, people certainly seem to think so. So at the time of all three of these gentlemen, Kirchhoff, Stewart, well, Wien, and Planck, people assumed that the sun was also some sort of a black body. In other words, it was a solid object. It had a crust at least. And so they actually thought people lived inside of those little holes, actually, not that long ago, something like 200 years ago. I mean, it was kind of a foregone conclusion. So people treated the sun as if it was a perfect black body. Yeah, well, not only does its light fit on the curve perfectly as a black body, but it must be the true temperature because, well, why shouldn't it be? The sun's some sort of, solid-bodied, crusted thing. And so this made a lot of headaches later on because obviously we have convection cells in the sun. We see things moving. We know heat's being dissipated in other ways besides the rays of the sun at this point. Yeah. Yeah. Okay. I tried to explain that, but I probably wasn't very clear about it. So black body is the name of the process by which heated bodies give off a characteristic radiation. So solid bodies do this. Liquid bodies do this to some extent, although the temperature is going to be wrong because there's convection. And the hope is that gases do this as well. The problem is, though, all right, so when Kirchhoff came up with all of his black body equations, he speculated that if a body, depending on how much light it absorbed, you could basically put a scaling factor, you could put a number in front of it that would say how much light is taken up and how much isn't. Well, obviously gases don't absorb as much light as, say, a table or something, right? And so they're going to have a smaller number that scales that down. The problem is that no one has actually been able to reproduce the idea that gases can do the black body trick here on Earth. And so black body is just a kind of radiation that tells us the temperature of an object when it's heated, essentially, just by the way that its color looks, right? And the color is broken up into different frequency or different color, it's spread out here. So you have a lot more of this color, right? At the peak, I'm looking at the top curve. So a lot more of this yellow, and you have a little bit less of this red. And these are the power. This is the wavelength and how much power, how much intensity goes into each one of those. Am I making sense? Ask me a question.
So by body, are you referring to an actual object?
Yes. The sun itself, actually. Yeah. So this is kind of one of the tricks of understanding the sun is how can we make statements about its material character when we can't actually go there, right? So the sun is unbelievably hot, even at the surface. The atmosphere is supposed to be millions of degrees, right? There's no way to even stick a probe inside of that. It's so bad. So some of the best information we have comes from studying similar objects here on Earth and being able to deduce from those information about the sun's characteristics itself. That's what's so bizarre about this, though, to me. And I'm exploring this with you guys. Look, we treat the sun like a black body. This is really important because this gives us everything that we know about the temperature, about the different layers, the processes happening in the different granules, the spicules, all of this depend on the temperatures of the black body. But we've never been able to take a ball of gas and make a black body out of it here on Earth. This is troubling to me as an experimental scientist. Yes?
How would we do that? How would people try to do that?
Well, the argument is given that there's nowhere out, it's not possible to produce the pressures that are available on the sun. And so there's no hope of even pulling it off, actually. So there is this process I should mention. I was going to do it on Thursday, but let's do it anyways. There's this process called pressure broadening. If you squeeze a gas really hard, some of the lines, there does appear to be some sort of broadening of the lines. Remember, the spectra give off individual lines for gases, right? They have very few degrees of freedom. They can only rotate one way or the other or something like that. So they only give off one vibratory mode of light. Continuous bodies can wiggle in all sorts of ways. They give off continuous spectra. So there's been some demonstrated broadening of those lines, but it doesn't have this beautiful curve. We call this, the shape of this curve is a particular curve. We call it the Plankian curve, which is actually fitted onto the Plankian relationship that gives us the energy relationship to light. So by treating it as a black body, this is wonderful because it does allow us to move forward and say things about the energetic processes occurring at each layer that we're able to study. So we use a different kind of light to see deeper into the sun than we would use to maybe see the outer corona parts. Different wavelengths give us different information, but they're all confounded by the idea that that information is all of the information. So all of the light information is all of the information about the energy of the sun. This is perhaps a little dangerous because if the sun is not a true black body, well, there's two possibilities. The sun is a perfect black body, or the sun isn't a perfect black body. Both of them are absolutely troubling. If the sun isn't a perfect black body, then our statements about the temperatures and energies of the different layers are confounded, and the statements and the conclusions that we draw from that may be misled in some ways. And you might say, who cares, right? You might think, I don't care about the sun. Why is Dr. DeLay going on about all this? Here's the thing. Fusion power, right? You've heard of it before. If we want to move past burning stuff, if we want to move past having huge mountains full of radioactive waste, we have to develop fusion power on this planet. It's absolutely a must. If we want to visit other star systems, we have to develop fusion power. Now, I know there's been some headlines lately. Yay, we achieved ignition and stuff like this. These are very misleading headlines, actually. What they didn't tell you in these headlines is that, yeah, they were able to deliver a pulse of energy that resulted in the atoms being excited more than the pulse of energy. Fair enough, this is something of an achievement. What they didn't tell you is that it was something like 300 times that power necessary to actually generate the pulse in the laser in the first place, okay? So we are a long ways off from actually being able to generate and power our planet with fusion power. Now, here's my argument. If we don't understand the particulars of the energetics of the sun, because we're confused about this matter, we won't be able to understand how the sun does her magic, because the sun does fuse molecules, atoms together. It does release a great deal of energy in the process. And if we can figure out how to do that on Earth, we will be golden. People will starve less, the planet will be healthier, there will be less pollution, there will be less nuclear terrorism, right? Fusion is a very, very wonderful process. It doesn't make all the waste that we traditionally associate with nuclear power. So this stuff matters a lot. That's why I'm so passionate about it. Yes?
Wouldn't there still be a byproduct of the fusion reactor?
We can explore that a little bit. But yes, but they're not as nasty as the ones that we get today. The byproducts that we get from nuclear waste, particularly from refined nuclear waste, are essentially ready-to-go nuclear bombs. So that's a problem, and we don't have a good way of dealing with them right now. Like, I am a huge proponent of nuclear power. I think it's way better than burning coal and stuff like that. However, we don't have a good way of managing the waste from it. And not only is the waste gross because it's toxic, it's pretty much generates weapons-grade plutonium as a byproduct, which is not good, because if the wrong person gets a hold of that, it's going to be really bad for everybody. So there's ways around that. I don't know how fast we're going to solve the fusion problem. Of course, the people who are working on it are going to keep telling you that they're doing awesome, and I'm sure they're making progress in various ways, but I think that there are some serious fundamental misunderstandings about how the sun generates its fusion products. And I think this all starts with this idea of the continuous spectrum. I think that it all starts with what we're doing, because the fundamental problem with fusing atoms together in laboratories on Earth is that they're very hard to control. You take a bunch of gas and you try to hold it in place and squish it together. The gas just wants to go everywhere, right? Now, there's other ways of fusing atoms together. You can take actually a solid lattice and squish them inside of it, and you can fuse things this way. And there's some people working on that too. And I don't know if that's the way forward, but these are both very different processes that would require totally different technological applications. And if we are under the mistaken idea that the sun is a burning ball of gas and that the fusion starts there, when in reality the sun has some other phase, right? Let's say that it's actually more of a metallic object, right? Let's say that it actually has more of an onion layer than we think. Maybe there's a different way of approaching this problem as a result of that. So like I said at the beginning here, there's two possibilities. One is that the sun is a perfect black body. If it's a perfect black body, then it's probably not a burning ball of gas. The other one is that the sun isn't a perfect black body, and if it's not a perfect black body, then we have to adjust our black body calculations to account for the other processes that are draining energy, like the convection, right? Different ways of dissipating heat, different ways of dissipating energy. Either one of these is going to lead us back to a more appropriate conception of fusion, which is going to help the engineers out at the end of the day.
Probably a stupid question, but would the different environment of space, it's like not really one we live in, would that maybe be the reason why the sun seems to interfere with the idea of a black body?
Well, that's something of the argument that's given, right? So something of the argument that's given is there's nothing on Earth like a sun. There's no place, not necessarily it's space that's the problem, but the sun itself, right? We're talking about hundreds of thousands of times the mass of our own planet, right? Those kind of pressures that are thought to be fusing atoms at its core are beyond our ability to reproduce here on Earth, right? That's what's so amazing about this entire discipline, and you're not going to find this in other disciplines, right? Everything is theoretical here, absolutely everything. Everything. You hear guys like Neil deGrasse Tyson get up on stage, we know this, and we know that. They don't know, right? These are theories. Now, they're good theories. Some of them are really good theories and very compelling, but they're just theories, right? And what is a theory? Well, it's an explanation. Sometimes there's multiple explanations for one thing, but humans don't like that, right? We need to have one story that we tell ourselves about things that we can all agree on, right? And this is where this idea of consensus rears its head. Because generally speaking, if we need to make a decision like, oh, do we build the spaceship like, or do we build the nuclear reactor like this or like that? We want to have one solution to it, right? So we're very uncomfortable with the fact that that all we have is indirect evidence from these processes with stars, right? All we have is light. But the fact of the matter, which I hope that you just caught when I said it earlier, is we don't have a material conception of light in the consensus worldview. There's no, light is treated like whatever people need to treat it like for their equation. You can treat it like a particle, you can treat it like a wave, you can do all this stuff, but there's no material conception. So all of our evidence comes from light, and we don't really know what light is in the general conversation. So it starts there, and it just kind of goes off the rails. And I don't mean to say we know nothing. That is absolutely incorrect too. We know a lot in a sense that we have a lot of ideas about what could be happening in each one of these processes. But as far as certainty is concerned, we couldn't be farther from it, especially in something like astrophysics. Before I went to grad school, I worked in biomedicine. And biomedicine is a place where you actually do get answers, right? You can do an experiment. You can take some cells, put them in a dish, see how they react to this molecule or what that molecule, put them under microscopes, tear them apart. You can really play with things. But the stars, all we have is light. That is it. And we don't know what light is. So we're really, really at the edge of our understanding with these things. So again, my goal with this class is to explore things that I think are exciting. To me, that's going to make it a much more fun process for all of us. Your textbook's going to give you a standard narrative of these things, right? And I hope that I've touched on it enough so as not to alienate that narrative, right? It's a reasonable narrative. But there's a lot more interesting holes in it too. And then those are the holes that people like you, let's say you decide, I know most of you are non-science majors, but maybe even one of you will decide to go into science, right? I put these lectures online, by the way. They'll all be on YouTube if you want to watch them later. Let's say you miss a class or something. People watch these. Maybe somebody out there thinks, oh man, that's a really cool issue. I'm going to go work on that. Maybe, Somebody has to address the holes in the science. That's where all of the inspiration, that's where the future progress happens. When I went to grad school, the first thing that my advisor said to me was, find a problem that hasn't been solved. It's like, gosh, where do I get one of those at? Seems like everything's been solved. I feel like these textbooks say we know how everything goes. So it's really important, I think, when you look at a piece of nature, to look for the things that are debated, to look for the things that are confusing, the things that don't make sense, because maybe they actually don't make sense, and that's okay. A lot of times people, especially scientists, have a tendency to use big words and talk their way around things they don't understand because it's embarrassing not to understand something. And I understand that. I hate to not understand something, but it's a good place to start. So it's one of the best services we can do is actually admit when we don't understand something. There's no stupid questions. I appreciate you saying that. But in all reality, if you don't understand something, raise your hand because somebody else doesn't understand it too, or I haven't done a good job of clarifying it or something. So it's okay. That's actually one of the most important things, is that we don't understand stuff, and that's why we're here. That's why we do science. All right, so let's see here. We got 15 minutes left. Let's make it through the rest of the little details of the sun. So back at the surface, the effective surface of the sun, this word surface is a really interesting concept. I think that a surface is actually what defines a body, right? If you think, what is a body? If physics is the study of the interactions of bodies, then what is a body? And I would say a body is something that has a surface, right? It's defined by its surface. So you say, what's a surface? Well, a surface is something that separates the inside from the out. And so this word's going to pop up over and over again in your textbook. The photosphere is the surface of the sun. So it's a boundary that separates the inside from the out. But we also read that the sun has no true surface. And so this really bothers me. But when we say surface, what we mean here, in this case, I think what is meant in the consensus picture is that this is what we see, right? This is where the light emanates from the sun, okay, for the most part. Now, the photosphere, despite the fact that it's alleged to not be a true surface, it has some really interesting surface features, right? It has these little blobs, which are called granules, in it. And this granulation is really interesting. These things are huge, like 700 to 1,000 kilometers in diameter. That's like something like the size of Texas. The darker places are thought to be cooler. The lighter places are warmer. And it's thought that these are essentially rising columns of gas that are then settling back down. And these granules actually last only like 5 or 10 minutes, which is crazy. Some of them are enormous. There's some that are as big as a couple of Earths, and they can last for like 24 hours. And so, these surface features are transient. They're there, and then they're gone. There's not really a way to go and touch them. It's way too hot. You couldn't make it through the atmosphere even if you wanted to. So again, we're looking at indirect light to get a grip on this thing. Actually, the gases extend far beyond the photosphere, and we talked about the chromosphere a little bit. But this is the area right above the surface of the sun, where you see all of these little flares and flickers. We call this the chromosphere, and it's actually like 2,000 to 3,000 kilometers thick. It's quite large. The strangest thing about this picture too, I really try to inventory things that are weird to me, right? What's really weird is that the chromosphere is about 10,000 degrees Kelvin. The surface of the sun is about 6,000 degrees Kelvin. This is really weird. We're going to talk about the theoretical model for how that happens later. But I do want to mention it. The chromosphere is quite warm, and actually the temperature just goes up from there. Chromosphere also has these really lovely little whiskers. This isn't a great picture of them. These are thought to be convective processes that extend. They're thought to be gases. Actually, here's a better picture of them. You can see these little whiskers. There's some interesting confusion about these whiskers too. They do appear to have some molecular interactions in them. That is to say, they do appear to have some condensed matter in them. There's different lines that are only possible through chemical interactions. And so I would look to seeing more headlines about how these things work in the future, because again, if we're trying to explain the surface of the sun, we need to look for surface features, right? And I think that the structure and architecture of this is coming more into play. Oh, this is a good picture. So this is, I think I pulled this from your textbook, maybe not. So here we are at the surface of the sun, and here we are at a great distance from the sun in the atmosphere. This is temperature. This is very, very strange. And I don't want to peel apart how this is thought to happen yet, but essentially what we're getting into is this temperature at the photosphere is being measured from black body information. This temperature over here in the sun's outer atmosphere is being taken from the ionization energy, right? The energy of that electron transition in those gases that are out there, right? So these are two very different processes that are going on to give us this temperature. And so we'll play with that more in subsequent days. I want to make sure we make it to our history. Talked about that. Oh, sunspots. Okay, this is probably a good thing to wrap up with. So sunspots are one of the features that you can actually see from Earth. If we were to set up a telescope right now, we could project the image onto, say, a sheet of paper. We'd actually be able to see these little spots. And, people have been observing these things for centuries, actually. For a while, they thought they were passing bodies on them of some sort. But more recently, we've come to understand that they're actually holes in this effective surface. And what's really interesting is that if you track the appearance of these little holes, there seems to be a pattern to it. It seems to be something like a 10 to 11 year pattern to it, by which a bunch of these little sunspots are appearing and then disappearing. And you can see a picture of that here. I think I pulled this one from your textbook. Come on. Nope. Okay, so essentially the sun is awakening and sleeping on a 10-year cycle. And what we find is actually that the magnetic activity of the sun follows this. So the sunspots actually turn out to have a magnetic pattern to them, right? And I don't have time to explain magnets to you right now, but I promise you we'll do magnets soon. And what happens is that these sunspots, as the magnetic polarity of the sun changes every 10 years, that is, the north becomes the south, the sunspots subdue and reappear. And when they reappear, their leading edge is of a different polarity than it was in the previous 10-year cycle. Now, you might think, why is this important? Well, what's really interesting is that there seems to be some sort of correlation between sunspot activity and climate and weather here on Earth. And this is very poorly understood, but it's starting to get a little bit of attention from NASA. And I had the pleasure of speaking with one of the directors of the the Heliophysics at NASA a couple of months back, and they're just starting to work on this process of how the magnetic activity of the sun, the electromagnetic processes, interact with our own atmosphere, the upper layers of our atmosphere, which then can influence things like precipitation, maybe even things like volcanism and earthquakes. I mean, it's just a really fast, oh, here's the picture I was looking for. Please work. Nope, come on. So one thing people noticed was that not only is there a 10-year cycle, but there appears to be a bigger set of cycles too, right? For instance, back in the 1600s, there was, close to a century with almost no sunspots at all. And this was really interesting because this period was also a time of exceptionally low temperatures on Earth, right? They actually called it the Little Ice Age. And so this was kind of the first, and of course, this is a correlation, right? This is something else that's worth mentioning, right? When we're trying to understand nature, we're always looking for patterns. I would say humans are essentially pattern-finding machines. And so we go out there and we say, by the way, I believe this black line is the temperature, average temperature. And I'm not sure how it's scaled. Oh no, that's sunspot number, I'm sorry. But temperature followed really nicely with this pattern. And so people began to think, okay, maybe there's something going on. And it's actually taken us hundreds of years to get around to actually coming up with any models that could possibly explain how this is happening. And of course, it has to do largely with how clouds are made, right? Because, if you think about it, the clouds, if it's cloudy outside on a warm summer day, it actually feels pretty nice. It kind of can get cold, especially if the air is quite dry. So the ability of the electromagnetic interactions from the sun to affect the upper atmosphere do have an available mechanism for how this could happen. And this is really something that we're just beginning to study right now. So I think what I'm going to do is put a pin in it for today because I want everybody to have a few minutes to fill out the attendance sheet. Next time when you guys come in, please sign the attendance sheet on your way in. And otherwise, assignments are due Saturday. I'll post some Moodle right now. Guys. Thank you. Yeah, thank you.